Welcome back for part 4 of the Building Science for Dry Climates video series with Franklin Energy. In this video, we're going to discuss typical building assemblies that affect the pressure and flow of air in a home and the science of measuring a home's total air leakage rate. Be sure to watch the other videos in the series. They're presented in a way that's meant to inform your approach to delivering affordable, comfortable, energy efficient, and safe homes to your customers. This chart basically says it all. As energy demand has grown across the rest of the United States, California has kept the usage per person demand relatively flat. But how? By embracing energy efficiency. Even with the average size of new homes drastically increasing and the increase in the number of typical appliances like microwaves or the numbers of televisions, computers, cell phones, the list goes on. It's through technologies like more efficient space heating and cooling, and better window construction, more efficient lighting and refrigerators, higher R values, and better sealed ductwork that have all helped. Retrofitting existing homes and businesses with these same measures has been a critical part of the strategy as well. And this video series was designed to share what the experts have found to be the most effective and affordable ways to improve a home's level of energy efficiency. So in this video about pressure and airflow, let's first focus our attention on aligning the pressure and thermal boundaries. When you look at comfort, safety, and efficiency, these 6 points need to be purposely sought after and achieved. A thermal envelope that is fully insulated, a well-sealed air barrier, and that continuous thermal envelope needs to be in contact with or aligned with that continuous air barrier. In addition, you'll need to have efficiently, properly sized equipment to condition the living space and heat the water, a well-designed and balanced air distribution system, and healthy indoor air quality. The thermal boundary is what limits heat flow between inside and outside. It's easy to identify by the presence of insulation. The location of insulation, whether vertical in a wall or horizontal in a floor or attic, should be in contact with the air barrier. Even small areas of missing insulation are critical to address. Building scientists have found that voids of as little as 4% can reduce the effective R value of R19 by up to 30%. The air barrier is what limits airflow between inside and out, and the heat and moisture that's carried by that air. It's more difficult to identify than a thermal boundary because it can be hard to see, and it's not always where you think it is. We can use a tool called a blower door to locate and assess the condition of the air barrier. For maximum efficiency and comfort, the thermal and air barriers must be continuous and in contact with each other. The trick to this seemingly simple approach is that we know our building assemblies like floors, walls, and roofs don't allow us to paint this pretty picture, a continuous yellow and red line around our conditioned space. Deficiencies in the thermal barrier work the same way. Sometimes as simple as the attic access hatch, missing the insulation allows heat to escape in the winter and enter the home in the summer. This is a surprisingly common symptom, but a perfect illustration of a gap in the insulation. Interior walls and mechanical chases can have deficiencies in both the thermal and air barriers. Fiberglass insulation does not stop air from flowing through it, so dirty spots in the insulation can be signs of penetrations in the air barrier below. The insulation filters the air, collecting the dirt, dust, and moisture as the air passes through. Built-in cabinets of older homes can be the source of significant air leakage. A view of this from inside the attic would reveal this, an extreme case of an attic bypass where outside air moves freely from above and below the home. Can you see in this picture that you can actually see the contents of a drawer down there from inside the attic? And the client wondered why her silverware got cold in the winter. That dramatic case of a bypass is now sealed at the floor level of the attic. Sealing at this level allows for easy alignment of pressure and thermal boundaries without filling that entire cavity, including the silverware drawer, with insulation. The shielding or dam around the chimney prevents cellulose or other insulation materials from coming into contact with high temperature surfaces. And when done properly, the attic now looks like this. So there are other construction details that result in gaps in the pressure and thermal barriers. I jokingly refer to them as the common culprits, but they're things like changes in ceiling height, knee wall attics, walk-up attics, and drop soffits. This drawing shows how changes in ceiling height can create gaps in the thermal and pressure boundaries. The top of that wall is uninsulated. In the winter, heat will flow from the conditioned space through that upper section of wall, through the break in the thermal boundary, and up into the attic. But not only is the top of the wall uninsulated, but the interior wall cavities act like a chimney that can rob the house of heat and conditioned air, allowing it to move freely up through the stud bay. There's no top plate to prevent the warm air from escaping. In older homes, the ceiling level changes in closets, causing gaps in the pressure and thermal boundaries. The uninsulated bedroom and bathroom walls are exposed to essentially the outdoor temperatures. Here we see the use of rigid foam board to plug these large areas and spray foam to air seal the edges, creating a new air barrier at the floor of the attic. New insulation will be blown over the top, and you get, voila, the pressure and thermal boundaries are now continuous and in contact with one another. This drawing shows a change in ceiling height and a drop soffit, another common culprit, which creates two causes for the breakdown. Even without a change in ceiling height, drop soffits cause misalignment in the pressure and thermal boundaries. The pressure boundary, which is the sheetrock, drops below the level of the attic floor and is not typically sealed at the top, which again creates a void in the insulation and allows air to move freely in and out of the stud bay. So locating the thermal boundary could be relatively simple with a visual inspection, but using a blower door to measure the condition of the air barrier is an effective way to determine the potential for energy savings with sealing. By blowing air out of the home, we can create an artificially high amount of depressurization, which exaggerates the amount of air leakage infiltrating through that home's air barrier. Blower door fan speed is controllable and allows us to create specific pressure difference between inside and outside by dialing up the fan speed till we reach the intended target of 50 pascals pressure difference. And since we're depressurizing, we refer to it as negative 50 pascals inside with reference to outside. We'll get a lot deeper into the details of blower door testing later. But with the house set to this negative 50, we can also use our manometer, a sensitive pressure gauge seen in these pictures, to compare pressure differences in different parts of the house. Zone pressure diagnostics use the artificial pressure in a home to test the connection differences in zones of the house. Using a small metal tube, you can poke up carefully through the corner of your attic access, essentially leaving it closed, but still get a reading of the attic pressure with reference to the house. And since the attic should be connected to the outside air, you should read a 50 pascal difference between the attic and the house. If it's less, then you're essentially measuring how much connection there is through the air barrier. The house could be literally depressurizing the attic through those holes. When you probe interior walls and other interstitial cavities, there should be zero difference if they're truly inside the air barrier. Small or large deficiencies indicate the presence of or severity of breaches in the air barrier. Plumbing chases often create breaks in the air barrier. Not only do penetrations like these increase a home's air leakage, they also reduce the R values in the nearby attic insulation. This picture gets me every time. Looks like an opportune electrician took advantage of an inaccurate plumber. Maybe I'm wrong, but it looks like the plumber drilled in the wrong spot or decided after the fact to move the pipe that you can see on the right. Later, an electrician ran some Romex down the big hole because it was there. No matter how it occurred, it's a large hole in the top plate and will allow for excessive air leakage through that stud. We're not trying to beat up on plumbers, I promise. They got to get their pipes through somehow, but you can see how plumbing chases can be opportune places to locate and fix penetrations in the air barrier. Another view of a wall with a chimney chase fully open to the attic. Like many things today, you have access to a wealth of knowledge through the internet, and building science has a strong online community. I want to urge you to take a few minutes and Google thermal bypass checklist. You'll find a well-written and well-illustrated document about Energy Star qualified homes, reinforcing what we've been highlighting in this presentation. But you can quickly scroll through photos of real-life examples of insulation and air barrier alignment failures, followed by well-done solutions for those same situations, giving you quick and easy ideas that you could implement to improve your own energy efficiency retrofit work. In summarizing this first section, you need to remember that to achieve maximum efficiency and comfort, the thermal and pressure boundaries must be continuous and in contact with one another. Understanding that there are common building assemblies that are known trouble spots, like electrical and mechanical chases, missing top plates, knee walls, and drop ceilings. You can use a blower door and pressure diagnostics to determine the location and condition of air barriers. Zonal pressure readings in conditioned spaces should read close to zero with reference to outside, meaning that your interior walls, drop soffits, and other interstitial cavities should be all inside the pressure boundary. And if you locate a problem area, you can target an air sealing strategy that defines the pressure boundary. So let's take a closer look at blower doors, what they are and how they work. Blower doors are a tool we can use to quantify and locate air leakage by using a calibrated fan to depressurize a house. All houses leak air due to naturally driven forces like wind, the stack effect, and even the home's own mechanical fans. But that naturally occurring pressure difference is too low and makes measuring air leakage unreliable. But with blower doors, we can exaggerate the pressure difference so the leakage can be measured reliably and those results repeatable. And from that exaggerated air leakage measurement, we can get a pretty good idea about the leakage rate under normal conditions. This slide points out 3 important rules of thumb you can use when doing blower door testing. I'd like to start with the bottom bullet. Blower door testing tells us a lot about a house. The test produces a number that represents how many cubic feet of air per minute are leaking. With very little experience, you'll begin to know how to interpret that number to tell which houses have the most potential for energy savings. Not all houses are super leaky, and the blower door can help you see that potential. Conducting blower door tests before and after air sealing helps determine the effectiveness of our work. Post-testing can also reveal whether any big leaks were missed. And the rule of thumb at the top is that The blower door test result can be roughly compared to the total size of a hole in that home, as though you could add up all the little holes and communicate that size as one large hole. We'll come back to this point later in the presentation, but it's a way of communicating the test result in layman's terms, something that your client will more easily understand. All three concepts are good reminders about the value of doing a blower door, where you measure and know what the building's air leakage rate really is. So let's get into the nuts and bolts of what we're actually measuring. We do not measure total pressure, but the pressure difference between one space and another. Always one pressure with reference to another. Sometimes we measure pressures under controlled, artificial conditions, sometimes under normal operating conditions. And it's important to communicate which condition your numbers are reflecting. I said this earlier, but the blower door uses a fan with a dial that controls the speed of the fan and allows us to create a specific pressure difference between inside and outside by dialing the fan speed up until we reach the intended target of 50 Pascal pressure difference between inside and outside. We refer to it as negative 50 Pascals with reference to outside. If you're new to building science, and you're anything like me when I was new to building science, you might be asking yourself, what the hell is a Pascal? Well, the non-scientific way to say it is that 1 Pascal is equal to about the weight of 1 Post-it note, meaning not so much. And you should also know it's a metric standard of measure. HVAC folks are oftentimes familiar with inches of water column, which is an American standard. Well, it takes 249 Pascals pressure to equal 1 inch of water column. 1 inch of water column is equal to the pressure required to suck 1 inch of water up a straw. We perform the blower door test, depressurizing the house to a point where we've created 50 Pascals of pressure difference between inside and outside the home. Terms that we use to communicate measurement of airflow include cubic feet per minute natural, or CFM-N, to represent normal conditions, and CFM-50 to represent airflow measured with the blower door running. CFM-50 is how we communicate the blower door test results. Parts of a blower door include the fan itself, the frame, a speed controller, manometer, which is the pressure gauge, and the hoses required to give the reference amounts of pressure. These are two of the most popular brands. The left photo, the Minneapolis brand from the Energy Conservatory, and the right photo is the Retrotec brand. I want you to notice the white plastic rings on the face of the Minneapolis on the left. It has the A ring on it, which is common for testing average size homes. You can remove that A ring and test with the face of the fan wide open. That's common for bigger and leakier homes. And you can also add the B ring to accurately measure smaller and tighter homes. You, the auditor, get the opportunity and responsibility to do what's best for that particular house. Blower doors come with an adjustable frame that assembles and disassembles for easy storage. In this middle picture on the bottom, you can see a 3-sided knob for loosening and tightening each of the expandable pieces of the frame, as well as a lever locker behind it, which strengthens the locking mechanism with extra pressure to help hold the door in place. And this is what it looks like when it's installed in a door. What you can see in this picture is that the red canvas door has a round viewing window to see anybody might be outside during the test. And you can see just to the left and up a little from the window is a manometer. That's the gauge that allows us to simultaneously measure pressure in the house with reference to outside, as well as the amount of cubic feet per minute going through the hole in the fan during the test. In this picture, the manometer is attached to a bracket on the side frame, and the white circle on the bracket below the manometer is the fan speed controller dial. That gives the technician doing the test the ability to speed up the fan till the target pressure of -50 pascals is reached. The older Magnehelic gauges, like the one on the left, were the original technology used in the development of the blower door, but have been replaced with digital manometers today. The DG700 used with the Energy Conservatory brand, and the DM2 used with the Retrochip brand. And while the DG700 and DM2 have been the industry standard for decades, the DG1000 and DM32 are the newest products on the market. They're Wi-Fi enabled for easy test result recording and can be controlled with your cell phone. Let's look at the steps for setting up the house to conduct a blower door test. Now make sure you start putting in an exterior door. It's important to put the house in winter mode, which means closing all the exterior doors and windows and opening all the interior doors. It's important to turn off the heating and cooling system as well as the water heater, especially particularly a gas-fired water heater. We typically put them into like vacation mode or pilot mode. Close the fireplace dampers. Definitely don't want to have any wood stoves in use. And it's good practice to check for ashes bottom of a fireplace. Either remove them or cover them with a newspaper. You could get a lot of wind coming down that chimney. If it's a pile of ashes, they might just end up in the living room. So with the house set up and the blower door ready, we can focus our attention now on the manometer. I want you to notice the green hose and the open pressure port labeled input just above it. These are like two little scales, and we call this the A channel. The reading on the screen above the A channel reads the pressure difference between the two scales. The green hose to outside allows the pressure ports to compare the input house pressure to the reference outside air pressure and shows us a reading on the top left screen. The red hose on the B channel goes to the fan and transfers the fan pressure as an input with reference to the house. The fan pressure in the red tube comes from the airflow across the sensor in the hub of the fan. The manometer compares this fan pressure to the pressure inside the house and converts the pressure difference to a rate of airflow. Some things to know when performing blower door tests include how to use the low flow rings for tighter or smaller houses. I touched on these a few slides back, but they give you the options so you can get the most accurate reading. If you're testing and the airflow pressure across the sensor is too low, the manometer will flash a signal at you and you'll know you're too low. And by adding a ring, you increase the pressure across that sensor in the middle of the fan. Another helpful option is the can't reach 50 function. In some cases, you might test a house that's so big and so leaky, you can't depressurize it all the way to -50. With the fan wide open, if you're at full throttle, that's all the pressure you're going to be able to get across. The older manometers came with tables and multipliers to help adjust the airflow readings based on the highest pressure you could get. But the new manometers can do this calculation for you. Checking your flow sensors is critical as well as your rubber hoses. Watch for kinks and other obstructions. And lastly, be sure that your reference to outside hose extends out and away from the jet stream of air created by the fan. I try to get my hoses 10 to 15 feet out of the way around the corner if possible. The flow sensor is basically a plastic ring with 4 holes in the center of the fan. A tunnel inside the sensor connects the holes to a hose that extends to a tap on the top of the fan housing. When you set up the blower door, you connect your tubes to that tap to relay the flow sensor pressure to the manometer. The manometer has other important settings that you have to manually input with the buttons. Let's start with mode. The DG700 needs to know what kind of test you're doing. So you have to tell it that you're doing a pressure flow at 50 test, meaning it's only reading pressure on the A channel, but it's calculating airflow at a 50 Pascal difference on the B channel. The time average function usually defaults to a 1 second when you turn on the manometer, which just means the flow rate calculations are being given in 1 second intervals. You can switch to 5 seconds or 10 seconds, but most folks agree that the 1 second time average works best for blower door testing. Other settings include the device setting and the configuration setting. Because the manometer can be used with several different pieces of equipment, you have to make sure that it knows that the device you're testing with is a blower door. The configuration function is how the manometer knows which size of opening you're using on the fan in order to calculate the correct amount of airflow. The manometer needs to know the diameter of the opening on the face of the fan. Again, there are two plastic rings that you can use, the A ring and the smaller B ring, or the option to remove both and run the fan with the face wide open. It's critical that you configure the manometer to the appropriate opening size. With the manometer set up, the last thing to do before you turn on the fan is to measure a baseline difference in pressure in the house with reference to outside. Most folks give it about 5 to 10 seconds to measure the average pressure difference before the test. Then they set the baseline function to ensure that we depressurize to a true 50 Pascal difference. Now we can remove the fan cover, turn the blower door on, and slowly dial up the speed till you see that you've reached negative 50 Pascal difference between inside and outside. At that point, you read the whole house infiltration rate on the B channel. At this point, the blower door is running. We have the house at negative 50, and the manometer is telling us that the house is leaking 4,257 cubic feet at 50 Pascals. That's it. That's the house air leakage rate. Pretty cool, huh? But what does that really mean? Well, what we know is the CFM 50 air leakage rate of that house. But what we really want to know is the CFM natural or everyday normal air leakage rate. So the way we translate between these two languages is by using the N factor. The N factor can vary kind of based on your climate zones, or the numbers of stories of a particular house, even the exposure to wind. But you can take your blower door test result and divide it by the most appropriate N factor to get CFM natural leakage rate. Here's the N factor chart. There's a climate zone map from the folks at Lawrence Berkeley Labs for you to reference regarding your area. But most of Northern California, where I live, is zone 3. If I'm doing a typical one-story house in a neighborhood, I would consider that to be normal shielding from wind, and I would use the 21.5 as my N factor. Near the beginning of this presentation, it was said that the blower door numbers were comparable to the actual size of the hole in the house. So this slide is helping you to visualize what that means. It's like saying that if you did a blower door test on a house and got 5,000 CFM 50 reading, it would indicate that all of the small and medium-sized holes would be about 500 square inches. It's a way for you to visualize the air sealing potential of a house, and it also could be used to communicate the extent of the problem to a homeowner. You simply divide the blower door CFM 50 number by 10 to get the size of this theoretical hole. We've talked about a lot of details, but this is where the rubber hits the road. We still don't really have a handle on exactly what that blower door number means. But when you can convert it into the context of air changes per hour, it begins to make more sense. PG&E has adopted the target leakage rate of 0.35 air changes per hour, meaning If you find a house leakier than that, you should air seal it down to approximately that target number. To get there, when all you really know is the CFM 50 blower door test, you can convert cubic feet per minute to cubic feet per hour by multiplying by 60. You can convert cubic feet to air changes per hour by dividing it by the volume in the house. And you can convert the 50 pascals, pressurized reading to the natural reading by dividing by the N factor. So let's look at an example. Take a house with dimensions 40 by 28 with 8-foot ceilings. The blower door test result was 4,500 CFM 50. So the air changes per hour in natural conditions could be got by taking the blower door test result, 4,500, multiplying it by 60 to turn it to cubic feet per hour. You divide that by the volume of the house at 8,960 cubic feet and divide it again by the N factor, which in this case, they're using the number 20. And you see a 1.5 air changes per hour. Well, that's a super leaky house. In fact, it's 4 times leakier than the 0.35 target that PG&E is looking for, which means there is a ton of opportunity for improved comfort and reduced energy bills by performing air sealing at that house. Let's look at a real life example. I've changed the house dimensions a little to approximate the size of the house that I was living in when I got my own first blower door. It was a 1,220 square foot house. It was 3 bedrooms, 9-foot ceilings. It's built in 1989, and it was a slab-on grade foundation. The blower door test result was right about 1,380 CFM 50. And when you plug that information into the formula to get the ACH natural, I was using the 21.5 as the N factor, but you get a 0.339 air changes per hour natural, 3.4 if you round it up. That's already tighter than PG&E's target of 0.35. That house was not a good candidate for air sealing. So I focused my energy efficiency strategies on other things like lighting, other base load appliances, even my own occupant behaviors. So in conclusion, the blower door is a device we can use to control a driving force that can also be used to quantify air leakage. Air leakage is measured in cubic feet per minute at a pressure difference of 50 pascals with reference to another space. Air changes per hour relate air leakage to building size, taking the volume of a home into account. Blower door readings can be used to communicate a building's leakage rate a couple different ways. It can be converted to CFM natural leakage. It can indicate the total size of the hole in the air barrier. It can even be massaged into an air changes per hour rate under natural conditions as well. Thank you. I hope that you will watch the other videos in the Building Science for Dry Climate video series, Franklin Energy.